Okay, and one more thing, just let me close this window, otherwise. Okay. Okay, good. Today, I am referring to this link, History of Earth's Climate. And this is a PDF which is accessible, available for download on Virtuale. This PDF is not public domain, so this is why you can't find the link directly from my website, which, as you know, is open. Virtuale is reserved access, and therefore you can download the PDF from there. So this lecture, just 1 second, I want to put it in full screen, 1 second. I am almost there. Okay. Very good. Not very happy with the visualization, but I think it's fine. Okay, good. Okay, so this lecture was delivered in the past by Professor Veronica Rossi. She's one of the experts that I hope to invite also this year for delivering the lecture today. And she's not available, unfortunately, and therefore I'm delivering the lecture. I'm delivering the lecture because I think it is extremely interesting. I'm using her material because I think it's really well prepared, even if it's not open even if it's not in the public domain. Of course, I cannot fully substitute her. This is not precisely my field, so I rely on your understanding and your questions if anything is not clear, because I think that with your question I may try to be more efficient and more clear, but in any case I can bring your questions and reply next Monday if this is the case. What is the purpose of this lecture is to give you more information, better understanding of what research is presenting about the reconstruction of the past climate. We already discussed, we already introduced this topic, but we didn't go into the details. So today I want, starting from a very large window of the past and moving towards progressively shorter windows and located closer to present, I want to give you more information on how climate of the past is reconstructed and what we know about the climate of the past and what we don't know. This is important because you know, if we look at the past, this is an agenda of the lecture today, is a table of contents. This is interesting because if we look at the past, we can better understand the present and the future. And this is, you can see here a quote from a famous geologist, Charles Lyell, who was one of the founders of the so-called philosophy of uniformitarianism, which states basically, with respect to the context of physics, that the laws and the dynamics of the Earth system, the laws of physics, which are used to describe the dynamics of the Earth system, are not changing in time. What is changing is the forcing. What is changing is the boundary conditions. What is changing is the landscape. It's land use, it's human emission, but the mechanisms, the dynamics of the mechanisms don't change. This is a philosophy which, in this context of climate change, may help us to gain a better understanding of what's going on. Because if we accept the fact that the mechanisms are not changed, of course, by studying the past, by studying what occurred in the past, we can build our knowledge that will allow us to make predictions and, in the case of actions, to identify proper actions. So this is why we focus a lot on the study of the past. I am particularly motivated to stimulate this reflection because on the one hand, you may think that the past is not relevant. The past is something that already happened. We are, of course, interested into the future. So it may be questionable for our purposes to look at the past. It may also be questionable because indeed the forcings were different. So how the climate reacted in the past may be different from how the climate will react into the future. On the other hand, I think you get the concept that if we understand the mechanism, and looking at the past allows us to understand the mechanism. So if we use the study of the past for improving our knowledge, this is indeed something that may allow us to understand the future, even if the future will be different from the past. So from a philosophical point of view, I think it is important to provide the motivation for the study of the past. Okay, so Professor Rossi is a geologist, and therefore she's interested in particular in the geological footprint of past conditions of the Earth system. Geology can tell us how climate changed in the past. It's a sectorial view, of course, and it is like all disciplinary views may look subjective. So it's important that you understand, first of all, the big picture of the geological view. And what I mean to say is can be better conveyed with an example. Geologists look at the very long time scale, very long time scale. So their time scale is not the time scale of 100 years. It's not the time scale of 1,000 years. Their time scale is a time scale of several thousand, from several thousand to millions of years. And therefore, their view is a view that covers big changes in climate that occurred even before the beginning of the human history. And therefore, also their scale of change, it's a different scale. In global warming, we are concerned by a 1 degree of temperature increase. If you look at the geological time scale, as we already mentioned, we get remains of shifting temperature of like 15, 20 degrees. So indeed, their scale of reference is different, but precisely because it's different, it may allow us to understand what it can happen in extreme conditions. So it is important to look also at the situation which were characterized by big changes. It's important that we look at the periods where the Earth was without ice caps, because this allows us, as I said, to understand the extreme conditions. and to gain an understanding of now how the Earth system may react to the anthropogenic influence, even if the current change in temperature is much smaller with respect to what occurred in the past, in the pre-human past. So what are geologic records? It's given by sediments, by rocks, by rock formations. Sediments, of course, bring with them remains of the past climate. We will see technically how we decipher these remains. And also ice, glaciers, they of course trap water that they trap precipitation that occurred several thousand and hundreds of thousands years ago. These are the records that we try to explore. When we introduced this course, we called these records proxy records, because of course they are not direct observations. In most of the cases, in some cases we can call them direct observations, but in most of the cases, we measure in these geological records, we measure variables that are not directly related to climate. And then we establish a relationship that allows us from these records to move towards climate records. Okay, first of all, let's start with a very small introduction on our problem. There is no need to spend time on this because this was already introduced by me. We are concerned by the recent sea level change. We know already that we are talking about from 150 years ago, about from 15 to 20 centimeters of sea level rise. We are concerned by the temperature rise, and we know it's about 1 degree, 1.3. And we are concerned by the so-called Great Acceleration, which occurred after the Second World War. And I already told you that if you look for Great Acceleration on Google, you find a lot of information on what is supposed to be a sharp increase of the human influence on the Earth system, starting from the economic development that followed the Second World War. And this Great Acceleration gave the idea of suggesting that a new geological era was started by this Great Acceleration, which is called Anthropocene. We will have a picture in a few minutes about the succession of the geologic periods, and we will see that we are currently in the Holocene period. Now, there are some scientists proposing to start now a new geological period called the Anthropocene, and which is identified as the period when we can clearly see the effect of human activity on the dynamics of the Earth system. Actually, this idea of the Anthropocene is not liked by all the scientists because the previous period, the previous geological period, were identified basing on geologic remains, geologic traces of shifts in the climate, in the condition of the Earth system. And actually, some scientists say that there is not yet a clear sign in the geology. There is not yet a clear geological sign of the human influence on the Earth system. And it may be only a matter of time before we see this. But actually, I just wanted to report to you this idea, which in my opinion is interesting, because it raises the attention on the potential human impact and also the criticism. Keep in mind that any scientific innovation is usually accompanied by discussion and in some cases criticism. Okay, so let's then look at at our past. Here you see on the right the so-called instrumental period from 1850. We already mentioned it to today. And then you see that this window for a geologist is incredibly short. 150 years for a geologist is nothing. So this is why we want to refer to paleoclimate. We want to go back into the past. And here you see a pyramid of the geological periods. We are currently in the Holocene. The previous period dating back about 2 million years ago is the Pleistocene. And before the Pleistocene, we had the Pliocene, and humans can, the history of the human species began between the Miocene and the Pliocene, more or less. Of course, it was not, we don't have a fixed date, but if we want to go back to the origin of the human species, usually we go back from 5 million to 10 million years in the past. Okay, so how can we get an idea of the climate during this far past? When I introduced our conversation about 1 month ago, I talked about proxy data and I mentioned 3 rings, but actually 3 rings don't go back so far into the past. 3 rings go back, some of them are fossil remains of 3 rings, but we don't go back in the past for a long time. If we want to go back in the past for a very long time, we need to refer indeed to geological records. Okay, so let's see. Let's start from a very large window. This reconstruction of past temperature was proposed about 5 years ago. First, let me go back to the first slide, the title slide today. The title slide was proposing here on the right a figure that I have already shown to you. It's as well a reconstruction of the past climate, which goes back into the past for about 500 million years. So you may say that we already had this information. Actually, these reconstructions, as I already mentioned to you, are subjected to uncertainty. And by using a different proxy data, you may get different reconstructions. Maybe their pattern is more or less similar, but if you look at the details, you find differences. So here indeed, this one, which was presented, as I said, about 5 years ago, it's a reconstruction that looks a little bit different. And today is on the right. Perhaps an interesting issue is that in the extreme right, you can see the current raise of temperature. So it's also reported the global warming effect due to the Anthropocene, due to the human influence. And in going back into the past, if you compare this figure with the other figure that I have just projected on the screen, the previous one, you see some differences, but still you see some dominating features, which is the presence of hot period and the presence of cold periods. And another important feature is that within each extreme period, either warm or cool, you see that there are still up and downs. And the scientific literature calls interglacial periods both the big warm periods, but also the period within a glaciation where you have a temporary raise of temperature. And this temporary raise may last for 1 million years. So it's another important thing to notice here, but we already knew that, is that we are within a cool period now, a cold period. Even if we take into account the recent raise of temperature, still you see that we are in a glaciation, which is the Quaternary glaciation. We are not in the peak of the glaciation. Currently, we believe we are in an interglacial period. So we are in a period that is naturally warming. This is what we understood, naturally warming, but we have the superimposition of a human component, which may be very significant, because if we look at the past 30 years, we see an increase in temperature, which is significant, like 0.6 degrees, more or less. And this is very likely due, as we will see also in the next slides, to the human component, to the human emissions of greenhouse gases. But still take into account that we are during a glaciation, and there is a natural component of warming which is superimposed. Another interesting thing that is delivered by this figure is that you see in blue, the periods, the line is blue during the periods where the Earth had permanent ice caps. And you see that overall, in the past 500 million years, overall, the period without any ice cap were longer than the period with the ice caps, which is something that we already knew. Well, I mean, it was well known. On the other hand, it's not reassuring. It's not reassuring of the fact that the Earth system can survive even without ice caps. It's not reassuring, because when the human species and several other species of mammals proliferated in the last period where the Earth was equipped with ice caps. So we really don't know, besides temperature, what are the conditions of the Earth system in the period where we were without ice caps. They were. And we don't know if these conditions are still good conditions for humans. So it's not reassuring, but it is an important information to understand that in the past we had these situations with very high temperature. And it's interesting to try to understand what the reasons could be for this. What could have been caused the warming, the so severe warming that we know occurred in the past. So you see numbers in this figure, and these numbers are, first of all, before talking about numbers, some considerations which are reported here. So there are climate fluctuation on different time scales. This is important to understand. When we talk about variability, it's also important to gain an understanding, to gain knowledge on the time scale of the variability. So if we have cycles in temperature, it's important to know the length of these cycles, because it allows us to make predictions for the future. Actually, variability here is present at different time scales. I said that we have several up and downs, even without the warm and cool periods, there are up and downs, which means climate fluctuations on different time scales. Also, we have to recognize that variability is a normality, actually. So it is important. It is important because it allows us to make a better prediction. And also, I think it is important to understand that variability is a normality, because it means that actions are needed. Actions to mitigate and adapt to climatic variability are anyway needed. So on the one hand, it is clearly important to understand if the perturbations are given by humans rather than natural causes. But on the other hand, even if we accepted even if we knew the cause, in some cases the solutions wouldn't change, because in any case we would need to adapt to a variability that is normal on long time scales. And therefore, when we see that indeed something is changing, whatever is the cause, it means that we need to take action, to act. Okay, and also here you can see, of course, the greenhouse world started a long time ago. There were other greenhouse periods in the past, and now we live in a cool period. These are the considerations here, and also now about the numbers. So let's start from 5. You can see the steep rise of temperature that you can see there is due partly to the rise of temperature after the last down of the current glaciation. You know that about 11,000 years ago, the Earth started warming, and the warming up since 11,000 years ago is about 10 degrees. But on the other end, in the final part, there is also the warming of the great acceleration. This warming has been very rapid, because when we talk about half a degree Celsius, 0.6 in 30 years, it's very rapid, and it's a very short time scale. So one thing is to say 10 degrees in 11,000 years, which means 1 degree over 1,000 years on average. Another thing is 1 degree in 100 years, which means about 10 times faster. So, I mean, we are not sure that this rapid increase occurred also in the past. We cannot say no, but we don't have a so fine time resolution in these records. So, I mean, let's notice that the great acceleration is something that may be unprecedented, and this is a reason of concern. And then another important thing is that during the warm periods, we have geologic remains that tell us that there has been a selection of the living species. And in the period with the number 4, we had an extinction, a partial extinction of several mammals, those with the big ones, because in the warm period they experienced problems. And also with the number 3, you see the radiation of reptiles during another warm period. So, I mean, there are traces that we can get from the past that in very warm periods, we are talking here, you see the change in temperature. If we locate today on an average degree of 14 degrees, more or less, 14, 15, we have witnesses, we have records telling us that we got over 30, which means really something, I mean, that we hope to avoid in the future. Which means, but we also know that during these periods, very warm periods, living species experienced partial extinctions or total extinctions for some of them. So, I mean, there is reason to be concerned by very cold periods. Of course, also during very cold periods, living conditions for the living organisms were not as good. But also during very hot periods, during the opposite extreme, there are witnesses of difficulties and big changes in the dynamics of living species. And then with the number 2, you see that they marked these blue periods with the presence of the ice caps. So, in a way, this figure tells us some positive news and some negative news. The positive news is that the Earth system is trained to cope with extremes. But the Earth system is not the human species. It's not the living species. The Earth system is nature in its complexity. in its general conditions, but there is to say that in terms of the living species, which is, if you want, a subcategory of natural processes, a subcategory of nature, these living species during the extremes experienced problems. So good news and bad news. Okay, so I mean, probably climate change will not imply the death of the whole Earth system, but may imply some extinctions, some selections of the living species. By the way, the Earth system is not going to last forever. I mean, we know that in any case, planets and in their dynamics are continuously changing and are evolving towards very cold bodies for the reasons that we already discussed. It's a progressive cooling that annihilates the magnetic field, which means that the atmosphere disappears, and without atmosphere, the temperature goes down to very cool conditions like we can see now on Mars. Mars, we know that it hosted a lot of water. Probably it hosted life. We are sure about water, not sure about life. On the other hand, water disappeared after the probably magnetic field of the planet and the atmosphere disappeared. On the other hand, I mean, we are interested in a long time scale, hundreds of millions of years, but the processes that I was just talking about, so evolution of the state of planets, they are occurring on much longer time scales. So let's focus on the time scale of 500 millions of years, and let's try to better understand what caused these fluctuations, this variability. And it's very interesting also to try to understand how this information on past temperature has been derived, understand with more details. Okay, now nothing new here. Let's talk about paleoclimatic proxies and how these proxies are developed. Okay. So we already talked about sediments, sedimentary rocks, also rocks in general, also the magmatic rocks, the rocks originated by volcanic eruptions are interesting. They convey information on the past climate because these geological formation embed traces of the past climate. Let's see how. There are also marine sediments and for instance, marine corals and marine sediments. You can see here on the right, there is a picture showing a carrot of sediments that has been taken by the sea bottom. And these are interesting because in these sediments, we can find trapped isotopes. This is a term that I already mentioned to you. Let's try to understand now how isotopes are why they convey information on the past climate. This is something that I find very interesting. Here you can see an interesting map of an international ocean discovering program. These are drilling points where they took these carrots of sediments. And I would like to take your time, just 5 minutes, to show you this video, which is linked here, because it gives also an introduction to how these sediments, these drills are operated, and it gives also an introduction of the research, an important research project, which underlies several of these missions. And you see that the points are colored with different colors, and the different color indicate different research project. So let's just 1 second look at this video, and just 1 second. Let's see whether I can get into it. Let's see if I remember my password. This is the problem of teaching on a PC that it's not our own. Okay. Just 1 second again. If I don't succeed, I will profit from the break to set up this video. Let's see. Okay, let's move forward, and then during the break, I will set it up. So let's then try to understand how we can decipher the past climate from these marine sediments, but not only marine sediments, also ice cores, which are drilled on the polar caps. And let's see what is the information content that we can retrieve from these sediments. And let me just go, I jump forward here because I want to give you this information soon. So, isotopes. One way to get the information that we want from these cores, from these sediments, marine sediments or ice cores, is to look at the content of stable isotopes. It is indeed interesting. Stable isotopes are, isotopes in general, are characterized by a different number of neutrons with respect to protons in the nucleus of the atom. So, for instance, if we look at the oxygen, and we look at the normal composition of the normal number in the nucleus of the oxygen of protons and neutrons, they are in an equal number, and they are in a total number of I would say 12. 6 plus 6. We have an isotope when the number of neutrons is higher than the number of protons. It's carbon that is 12, sorry, carbon is 12. Oxygen is 16, 8 plus 8, okay? Carbon is 12. If you have a larger number of neutrons in carbon, for instance, it means that you have, let's say, 7 neutrons and 6 protons, and we call it carbon 13. And then we get to carbon 14, carbon 15. Carbon 14 is an isotope that you probably heard already about because it is used to date things, to date materials. Carbon 14, it is used to date things because it's a radioactive isotope. What it means radioactive? It means that during time, it tends to get to another content, a lower number of neutrons. So it tends, the number of neutrons tends to decline during time. And therefore, it's not a stable isotope. It's a radioactive isotope. Stable isotopes, they keep their nature a long time, which means that if we have an isotope O oxygen 18, it remains in its state forever, for a long time. Now, what's the difference besides the number of neutrons between O18, stable isotope, and O16? O18 is heavier than O16. So when this isotope of oxygen forms the molecules of water, these molecules are the molecules formed by H2O18. They are heavier than the normal molecules. And therefore, when they are in the ocean, they tend to evaporate later. So in evaporation, there is a preference for the evaporation of the lighter water molecules. So think of a situation where you have evaporation during a cool period. Evaporation during a cool period means that you have this flux of O16 in the atmosphere, and therefore the ocean becomes richer of O18. This happens anyway, okay, in both warm period and cool period. But let's focus on a cool period. You have still some evaporation. The evaporation brings O16 in the atmosphere. The ocean becomes richer in O18. And then you have a condensation of O16, which in a cool period is, after precipitation, trapped into the ice. So the ice is keeping O16 over the land. It doesn't go back to the ocean. In a warmer period, it goes back to the ocean. And therefore, the situation is re-established. In a very cool period, the O16 is trapped into the ice, and the ocean remains richer of O18. And therefore, the living organisms like corals, they absorb these isotopes of O16, and their body of these living organisms, like foraminifera, we will see the details, their bodies get richer of O18. So when we find in a layer of sediments remains of living organisms with a different content of stable isotopes, we understand that these living organisms, if they had more O18, lived in a cool period. And then we have the problem of dating, of course, because when we get a column of sediments, we understand that each layer corresponds to a temperature, but then we have to put the date into them. And then maybe that we need other proxies. But I hope it's clear the concept of the isotopic traces. And look at this slide. It illustrates how to compute what is called delta O18. Delta O18 is computed. Look at the relationship in the line below. Delta O18 is computed by looking at the ratio between O18 and O16 in the sample. So in each layer of the sediment, you find a ratio between O18 and O16 in the sample. Now you look at the same ratio in the current conditions. So there is a minus sign. So if you have more O18 in the sediment, this difference is indicating that the temperature was lower. So if the ratio O18 versus O16 is greater in the past than now, it means that the temperature was lower. And this difference is expressed in relative terms because it's divided by, again, the current ratio between O18 and O16. So in a way, different types of oxygen. One is heavier and the other one is lighter. In a cooling period in the sea, you have more heavy oxygen than light oxygen because the light oxygen after evaporation gets trapped into the ice. This is extremely interesting because O18 is stable, doesn't have a decay. And then we may use other isotopes like carbon-14 to date each of these sediments, even each sediment layers. So it's interesting. Now let me go back to the slides where I started. I started jumping forward because I wanted to introduce this. In this slide, before I leave it, you see also another delta on the right, which is the delta of deuterium, which is an isotope of hydrogen. There are several isotopes. We usually refer to the isotopes of oxygen, but we can use also isotopes of carbon, isotopes of hydrogen. There are several possible isotopes that we can use. So let me go back here. So we have these paleoclimatic archives. Some of them you see are located over the land, over the ice caps, and some of them over the sea. These paleoclimatic archives, most of them give data for free. So if you, for instance, here you see a link over these slides, there are several links of sites. We are not visiting them now because it is not an immediate operation to get data from them. You need to register, and also you need to to download the data and put the data into Excel or whatever, or MATLAB, and derive the information, the statistics that you need. But if you are interested, you can for sure explore these websites and try also to see their information content. And then, of course, they deliver different information. Let's try to understand what is the kind of information that we can extract. So you see here marine sediments, marine sediments give information about the chemical composition, stable isotopes. Also, the particle size is important because, and also it's important because the particle size is related also to the sea depth, to the condition of turbulence, because very fine particles are basically, they collapse over the sea bottom when the turbulence is very reduced. If you have a lot of currents, a lot of turbulence, these very fine particles remain suspended. And therefore, the particle size gives real information on the conditions. And especially in the water bodies that are less extended, like lakes or like big lakes. So it gives also information on the dynamics of the water body, the presence of waves, the presence of turbulence, etc. Another important sources of information is given by the speleothems. The speleothems are the minerals that are found in the caves, in the caves which were through percolation. These minerals which build the structures that you can find into the caves, stalagmites, etc. And there is a lot of information in these minerals because they bring with them water, and therefore they bring isotopes, they bring information on the type of precipitation. And then the ice cores. The ice cores also bring information on dust, the presence of dust, which is very important because it indicates volcanic eruptions, and also gas concentration. There is we can infer the concentration of the atmosphere from ice core, and again stable isotopes. We focus today on the marine sediments and ice cores. So we don't focus on lacustrine sediments and speleothems, but beware of the fact that also in lacustrine sediments, there is a lot of research ongoing, a lot of information that is continuously made available. Okay, so let's move forward here, and here we see an example of an ice core. Here there is, here you see links for links to interesting web pages where you can find additional information, which is presented in a very easy way. And these blogs of the European Geosciences Union are very educational and very interesting, and give you, as I said, additional details. Okay, now this is an example of a reconstruction of CO2 concentration for the past about 500,000 years, derived from ice cores. And indeed, what you can see here is that for at least 650,000 years ago, the concentration of the carbon dioxide has never been as high as today. From a geological point of view, this is a short window because we don't get to 1 million years, and therefore you understand it's very short if compared with the initial picture, which was extended. Temperature reconstruction was extended up to 500 years in the past. I mean, during the warm period without ice caps, for sure the CO2 concentration in the atmosphere was higher than today. This is clearly due to the fact that with a very warm atmosphere, we have a lot of release of carbon from the body of the Earth, from the oceans. On the other hand, the fact that we have now a CO2 concentration that was never so high in the past 600,000 years clearly emphasizes the fact that we are in a very atypical situation for the time scales, for the recent time scale, but still it's a very important time scale. We are talking about 600,000 years. And therefore, the concern is motivated. And also you see that from 1950 to the current level, there has been a significant increase. Of course, what you see in the final part, in the extreme right of this line, is reconstructed based on measurements. What you see in the past is reconstructed based on proxy data. Proxy data may average out extremes. But on the other hand, it's clear that from 1950 to today, the concentration raised from about 300 to 400. So we are getting close to the 2 CO2 situation, which is considered to be something to pay attention to. And this is an example of a reconstruction that was derived from a Vodstock carota. It's a carrot, ice carrot called Vodstock. Was presented as a reconstruction already 20 years ago. Okay, and here we have this research project, HEPICA. There is also a video, and we will take some time to watch it, which presents this project that aims to retrieve a continuous ice core to bedrock in Antarctica, covering the climate history of the past 1.5 million years. There is indeed a lot of research ongoing on this. Here there is the slide that we already saw, and here is a further explanation. And here you can see it's written down the conclusion that I already drew. When delta is positive, the sample is enriched in heavier isotope. When delta is negative, the sample is enriched in lighter isotope. Okay, now here's, you can see with a smaller window, it's about, the length of the window is about, just 1 second, it's the left ones are extended to now, and which is the 0, and 800,000 years, so less than 1 million. And the other one is it's same thing. And here we focus therefore on a shorter time window where we see oscillations that range in the range of 5-10 degrees, depending on the climatic reconstruction. And here you see the figure on the right shows oscillation in the range of 10 degrees. This is the range of oscillations in this time window. And you may remember that since the peak of the last glaciation, we had an increase of temperature, which is comparable to these statistics. And these have been all derived studying isotopes. Now, let me talk a little bit more about the foraminifera, the living organisms which absorb, these are living organisms into the sea, they absorb in their body these isotopes of oxygen or other isotopes. And these are the remains, the fossils that we study in order to get information on the past climate. when foraminifera calcifies, many environmental information of the surrounding water is stored in the chemistry of shells, including, as I said, the temperature. And these are indeed, these are interesting, very interesting information. And what is interesting here is that we can get information on a very good resolution. The sampling frequency, which means the time resolution of the information is very fine. We can get also seasonal indications. So indications which refer to the seasonal distribution of temperature. And it justifies why we are dedicating so much resources to ocean drilling. Here is another example from marine cores and ice cores. It is very useful to couple them together because in a way they confirm each other. So as I said, when you get a cooler period, you have the light isotope, which is trapped, the light oxygen, which is trapped into the ice, while the heavier oxygen remains into the oceans. And therefore, it's important to couple this information, to integrate, to put together. And you see, in this case, you get different indications of temperature. This, of course, because the ocean is warmer than the ice caps. So the information that we get shows a temperature difference, which is fine. But you see also quite a good agreement. This is a research that is has been presented, showing reconstructions from several marine cores and ice cores. And you see that indeed there is a good agreement. And this reconstruction allows us to quantify what is the difference in temperature of the ocean with respect to the ice caps. And this is a reconstruction that goes back 400,000 years, which was presented in 2007, about 15 years ago. And as I said, it's important to see the confirmation of what's going on. And here, confirmation is that means that when there is a cool period, in blue here, what we expect is to see a temperature effect. Colder means an increase of the delta O18 of shells, an increase of O18 into the shells, and there is more ice volume, more ice, and therefore we expect to see once again an increase of delta O18 into seawater and shells, and the presence of light oxygen into the ice. So this basically it's important to compare the responses from these different type of information. So the take-home message, which is shown here, is that the isotope records from the shells of foraminifera provide a quantitative measure of the combined effect of changes in ice volume and in the temperature of ocean water. So basically, we can get in this way a continuous record of climate history. And we already mentioned that when delta is positive, Earth was colder than today, and when delta O18 is negative, Earth was warmer than today. And this figure explains what I anticipated. So in a warm period on the left, you have evaporation from the equator, from the oceans, and preferential evaporation of light oxygen, like in the right. But then you have condensation. Keep in mind that some heavier oxygen still evaporates. There is a dominance of lighter oxygen in evaporation, but there is also an evaporation of heavier oxygen. And the heavy oxygen precipitates closer to the sea than the light oxygen, because condensation is favored, because it's heavier. But the big difference is that when there is a lot of ice in blue in the right figure, you see that there is the light oxygen trapped into the ice cap, into the glaciers, and then you see on the right figure in the ocean, the ratio delta O18 is positive. So we can locate in this way interglacial periods and glacial periods. Of course, here we see two extremes, a lot of ice and no ice, but we can also decode, we can also locate periods with a reduction of ice coverage, because there is more water into the sea, and we can decipher through the isotope concentration the extension of glaciers and temperature. The problem is that a lot of resources are needed for these drilling operations. You can imagine researchers need to equip a vessel and rent a vessel, equip it, and stay into the ocean for weeks. I talked with a person that is working on these missions. Actually, I asked to be invited once, because for 1 week, I think it's a good experience. It's a little bit, it can be tough, because in adverse weather conditions, you need to be trained to stay on a vessel which is not a huge one, in sea conditions that are maybe a little bit turbulent, which, it can be tough. But I think for 1 week it would be a nice experience. And, but it is really demanding. It's demanding in terms of personal effort and in financial terms. And of course, there are also some criticism, because this means that these significant resources which are dedicated to science, and the science is not always successful. There is, of course, some criticism when you are in a difficult economic situation, so you have to be very conservative in the allocation of resources. So there is the question of to what extent we should push our knowledge. Of course, knowledge is always useful. On the other hand, when it's costly, you understand that sometimes it's a difficult decision. Who is working in science, of course, it's very passionate and motivated, and indeed, I think that knowledge is worth getting. On the other hand, I recognize that it's allocation of resources should be based on a careful assessment, preliminary assessment, and accounting, because we are talking about very important finances. Okay. Now, when we talk about paleoclimatic proxies, we make a difference. We call them direct or indirect. The use of the term direct is to be understood in the context of proxies. We never have a temperature measurement which is a direct observation of temperature. It's always, there is always a mediation. But on the other hand, we call the proxies a direct proxy if we can detect tracers like dust or atmospheric gases, which are directly trapped into the cores, directly trapped into the ice caps, for instance. I mentioned dust. Dust is a good example. Dust is a direct proxy. Indirect when a calibration is required. What does it mean, calibration? It means that I need to compare, for instance, the difference in isotope composition with a known difference in temperature. Because otherwise, the only difference in isotope composition only tells me that Earth was warmer or cooler. It doesn't tell me warmer of 10 degrees or, and then, of course, we have to try to relate different isotope compositions with observations. And the obvious thing is to make a comparison with today, but this is only one point. So I have an isotope concentration given by the last layer of sediment. I know that the last layer has been formed 100 years ago. I know the observed temperature of 100 years ago, and this is a relationship. I can establish a one-to-one relationship between isotope composition and temperature, but this is one point. And therefore, I needed to find other information to make calibrations. Calibration means I relate the stable isotope values with a temperature value. And therefore, I establish this one-to-one relationship. And you understand that direct proxies can be used to calibrate indirect proxies. Because direct proxies, they don't need calibration. But it is not easy to match things, and this is why we try to collect several proxies. Because, of course, the calibration must be performed by referring to similar conditions, similar indicators, because one thing is temperature, one other thing is dust. Relating temperature to dust may be impossible. So I have to find information that can be integrated. Here is another example of an interesting use of fossil records. What you see here in blue is the current distribution of this shell, which is called Arctica islandica, and another shell in yellow, which is called, this name is impossible for me to pronounce, Persistis thrombus latus. Okay, it's better if you read. And in yellow and blue, you see the current distribution of these valves, which are the blue one in cool regions and the yellow one in warmer regions. The current composition, the current distribution, which means that the blue ones live quite well in cool ocean, and the yellow one lives quite well in warm ocean. Now, we can find remains of these shells in the Mediterranean. For instance, the Arctica islandica has been found in the late Pleistocene in Liguria, which means that at that time, in the late Pleistocene, Liguria, the sea, the Mediterranean Sea, close to Liguria, was cooler than now. And the yellow one has been found in Italy, again, in a different time period. So again, late Pleistocene, but if you look at the thousands of years ago, it's different. And therefore, this allows us to reconstruct the progress of temperature in the Pleistocene in Italy. Allows us to locate interglacial periods. So this is another way of getting information. It is not through isotopes, but it's just by studying the distribution of these fossils and considering their optimal habitat. I think this is another interesting example. Also, there is a lot of remains from vegetation paleo remains, and pollen. For instance, if you look at the current situation of vegetation in high latitudes, you see a different vegetation with respect to our latitudes. Different vegetation, of course, and we know also that at the local scale, as you go up in the mountains, the vegetation is continuously changing with a resolution that is impressive. I mean, when you walk in the mountains, you get like 500 meters elevation gain, and the vegetation changes completely. And the difference in temperature, on average temperature, you know that it's about 1 degree for each 100 meters of elevation gain. So it means that vegetation reacts to a difference in temperature of even a few degrees in a very significant way. And vegetation is living remains. So if we study the past distribution of vegetation, we get a lot of information. This allows us, for instance, to locate the climate optimum during the Roman Empire, and allows us to reconstruct the climate optimum in the medieval time. We can reconstruct these climate optimums through vegetation. In the medieval time, we also have remains from the witnesses from the monks, diaries from the monks. For the Roman Empire, we don't have this detailed information, but we have information on the historic reports, mentioning, for instance, the problem that the Roman soldiers experienced when traveling. And so we know that in some regions they found snow in a certain season, and this is important for reconstructing the past climate. But also we have information from vegetation. This is extremely relevant. So here Professor Rossi calls puts in evidence a possible identification of interglacial periods and glacial periods based on vegetation. Okay, now let's focus on another curve, another reconstruction. This goes back about 60 million years. This was presented again about 5 years ago. This reconstruction was presented almost at the same time of the reconstruction by Scott and Huber, which I showed you at the beginning of the lecture. But this is much more detailed. And Scott and Huber also presented it in a museum, and they didn't have time to formalize to illustrate the methods that they used. They also went in the past for a longer time. And I think the methods have been the same as reported here. This series, this reconstruction was presented in a sequence of papers. And here, what is interesting to notice is that they put together several different reconstructions by checking for their coherence and homogeneity. Several different reconstructions you see here. There is in the bottom of the figure, Epica Dome C is a reconstruction based on a particular set of ice cores. And then there is another reconstruction in the same period, the Lisiecki and Raimo, 2004. They put together these two reconstructions, and then for the other period is the same thing. You see that they put together a lot of information in an attempt to quantify also uncertainty, because of course coherence between different reconstructions highlights that there is less uncertainty, of course. And here it's interesting to notice the progress from a warmer period about 60 million years ago. And the warm period, if you indicate the current average temperature of the Earth, if you locate it around zero, you see the final part. And if you remove the period of the global warming, the final part of this figure on the extreme right is the global warming. It's the past 50 years. If you remove that period, you see that there has been a stable period starting from about 1 second. I think this is 10,000 years ago. Yes, it's 10,000 years ago. In the past 10,000 years, we have a relatively stable situation after the last glacial period, after the rise of about 10 degrees starting from 20,000 years ago. Starting from here, we had a rise. Here it's a little bit less than 10. It's perhaps 8 degrees. This last stable period is called the period of agriculture and civilization. Of course, stability, it favors the development of social communities, the development of stable settings, stable practices for producing food, etc. While changes, of course, force people to migrate, force people to adopt a more stable lifestyle. We will focus also on these changes that you can see here within the stable period. You see that there are fluctuations. Here is also reported the future projection. You see that there is in purple, there is an envelope diverging towards the future. This is given by the projections of climate models. And here you see the Homo sapiens period. The Homo sapiens period, the Homo sapiens is the current stage of evolution of the human species. Of course, humans existed well before the Homo sapiens. In fact, you see that the Homo sapiens period covers the past 300,000 years. But you still see that the Homo sapiens had to experience changes in temperature, which were, after the last glaciation, about 10 degrees temperature, which is anyway a useful indication, because it means that through migration, we know this, we know that the Homo sapiens migrated over very long distances. You have to understand that, you know, they, of course, could move in a longer time scale than now. But you have also to understand that migration, when it occurs on a long time scale, is easier than migration that is forced on a short time scale. It's much easier because, you know, the lifestyle has time to be adapted. Also, you have to think that the average duration of life for the Homo sapiens was less than 30 years. So they had generations, that the time for many generations to migrate. But still, it's an indication that the human species could afford, you see, jumps in temperature, which are very significant. Okay, let's move forward. And you see here that these jumps in temperature, just 1 second, yeah, the same figure. Jumps in temperature were characterized by warm interglacial periods and glacial periods. And even within the same glaciation, this is the same quaternary glaciation that we are living in now. But you see that even during this very cool period, there were fluctuation of temperature, or repeated fluctuations. And it's what is a little bit, if we take as reliable, if we take for reliable this picture, what is a little bit puzzling is the lack of any apparent regularity. So it is not easy to make predictions for the future in similar conditions, because this picture delivers a lot of information on the natural variability, but there is no regularity. So it is indeed, it would be very interesting to know some more about what caused these changes in temperature. We don't know it. We don't know if it was a volcanic eruption, if it was the impact of an asteroid, if it was a volcanic eruption, I already mentioned it. If it was a change in the inclination of the terrestrial axis for whatever reason. It's not easy to make, as I said, a prediction, because it's not easy to identify any regularity in this variability. Okay, let me make the break now. Do you have any question before I go for a coffee? Okay, good. Let's take 15 minutes break. Okay. What you can see here is a reconstruction of the shoreline during the last glacial maximum in the Mediterranean area. Corresponding to, as we know, because we already discussed sea level rise, corresponding to about minus 120 meters below present sea level. This was presented recently, and you see that indeed there are significant changes. On the other hand, probably you would expect something even more significant in consideration of the big step change in sea level. But on the other hand, there is to say that the Mediterranean Sea is quite a deep sea, and the Adriatic Sea has a lower depth. And in fact, you see in the Adriatic Sea that there is a significant advance of the land corresponding to a decrease in sea level of 120 meters. The Mediterranean, overall, we don't see big changes, even if, especially in the domain of in the east of the Mediterranean, you see close to Greece quite significant changes. Now, let me present another set of measurements. 57 globally distributed benthic records. Benthic means records of delta O18 in essentially in marine sediments, and also which with the purpose of measuring global ice volume and deep ocean temperature history during the last 5 million years. Therefore, covering the sequence of periods, of geologic periods, which extend during the Quaternary and a little bit of the Neogene, Quaternary plus Pliocene in particular. And this reconstruction, which is presented here, starts from now, from zero, and goes back about, here you see the picture going back about 3.5 million years. And you see that there is a progressive, stronger glacial signal through time. And there is a general cooling trend starting from now, going back into the past, which is what we were expecting for the first, let's say, 20,000 years. But also, if you go further into the past, you get deeper in the glaciation. So there is a general cooling trend. But on the other hand, you see here, thanks to the very fine resolution, that there is an impressive sequence of of short-term changes, which is really impressive because it means that indeed there is a periodicity in there, which we don't know the causes, but it's still clear that there is a periodicity. And therefore, this picture raised important scientific questions like how can we get a better understanding of these periodicities? How can we project this periodicity into the future? Because the previous picture that I showed to you, and the big one going back 60 million years, didn't allow to recognize these small-scale fluctuations, which are impressive for their I wouldn't say regularity, because we don't see like a cosine or a sine function, which is indeed extremely regular. But still, you can see that it looks like there is a superimposition of periodicities with different frequencies. And this clearly highlights that there must be something regular here, not a mere superimposition of casual events. So this figure is indeed raising interesting questions. And here you can see some consideration. And there is cycles that have a duration of apparently something like around 100,000 years. And they basically characterize a kind of 100 kiloyears world. And then there is like a transition interval which separates this green window from the yellow window. In the yellow window, the periodicity looks like something like 41,000 years. So it looks like the frequency of the up and downs is increased. And then for the whole duration of the yellow window, which goes back from 1 million years to about 3 million. And then we have the final part of the picture where it is difficult to recognize a regularity. It's more like the transition interval in brown that we see in the upper figure. So it may look like there are some period characterized by regular cycles, more or less regular, which are separate but with different frequencies. And 100,000 years, 41,000 years, separated by transitional periods. So maybe that they are caused by glacial interglacial cycles, maybe they are caused by the same regular changes that characterize glaciation, but it is really, and it is really difficult to get an interpretation. And it looks like we now live in a world that is characterized by seemingly 100 kiloyears periodicity. This is present, this is now zero. So, this figure is located here in, you see, it's corresponding more or less to what we see here, but with a lower resolution in this case. So, let's now look at the last 10,000 years, 10, 11,000. Are they so stable? So, we see from the previous picture that indeed the last 10,000 looks stable. But as I said earlier, let's look in more detail at this period. We are in the Holocene. It looks like, if we look at this figure here, there is still a climate variability that we can see in the Holocene, which look like some millennial scale climate variability, which matches also with the considerations that I made earlier on the climate optimums, the Roman the climate optimum during the Roman Empire, the climate optimum in the medieval period. So it looks like there was a warmer period around the year 0, 2000 years ago, and also a warmer period about 1000 years ago. Let's look with more details. And now, let's look at the map, these maps of climate anomalies during the event that occurred about 8,000 years ago, where we got a cold climate in the northern hemisphere. It looks like a warmer climate in the southern hemisphere, and a wetter climate where it was cooler, in particular in the northern hemisphere, and a prevailing distribution of drier climate, sorry, in the southern hemisphere. In general, what we can observe from the past climate is that cooler conditions are associated to better climate and warmer condition to a drier climate. And cooler conditions are associated to more floods, and dry conditions, warm conditions are associated to more droughts. So it looks like there is not a clear match with the current situation, where in the warming condition we observe apparently an increase of flood frequency, but we didn't observe a clear increase of drought frequency. But of course, the kind of information and the time scale we are considering is a bit different. Okay. Now, what about, as I said, the historical period, last 2000 years? Here you can see a picture of the Venice Lagoon in 1789. It was the year of the French Revolution, which you see people skating over the lagoon, which is something that didn't occur in the past 150 years. And on the left, you see a progress of temperature from the present, 0, to the past. You see the Roman warm period and the medieval warm period. They are separated by about 1000 years difference. And you see the cool periods, the Little Ice Age, which corresponds to the figure that you see on the right for Venice, and what is called the Dark Ages cool period, which extended from about 1200, 1500 years ago. By the way, this Dark Age cold period, there are some theories, some assumptions that postulations that assume that it contributed to the final collapse of the Roman Empire. Because as I mentioned in other lectures, in the recent past and with respect to the northern hemisphere, the Western world, we could see that warming conditions were associated to more wealth, easier conditions, environmental conditions, and cool periods were characterized by more relevant risks and a more difficult life. And this is also what remains from some historical reports from the Romans, which prove that a lot of resources were needed to recover from natural disasters, which contributed to the final collapse, economic collapse of the Roman Empire, which is something that may be indeed credible, because it matches with other reports related to the onset of the Little Ice Age, which caused a lot of disasters, an increase in flood frequency, and consequently the collapse of some administrations with which didn't have enough resources to recover from these natural disasters. Looking at the recent changes in climate is interesting. It's, you know, it's not easy because the information is, even if the time is relatively recent, the information is fragmented. And it allows, it's also not easy to try to understand what was the reciprocal forcing between the atmosphere, vegetation, ice, land surface, ocean. It's not easy to understand what were the causes for these changes. So what caused the climate optimum during the Roman Empire? What caused the subsequent cool periods? This is something that we still don't understand. And we try to understand what of these spheres that you see here. This is another representation of the land of the Earth system in spheres: atmosphere, vegetation, ice, ocean, land surface. We try to understand from where the forcing determining the change came. Here it's not specified, it's not shown the solar activity, which may be responsible indeed of these optimums, but there are other drivers that are being investigated, which I would like to explore a little bit with you now. So, causes, external forcing, changes, let me see if I skipped one slide, no. Changes in plate tectonics, and of course these changes in tectonics may be responsible of the shift of masses. If you have continents moving, you can we can assume that this shift of masses may cause a change in the inclination of the terrestrial axis. It may cause a change in the distribution of gravity, and therefore it may cause volcanic eruptions. And these are all perturbations that could have contributed to drive these climate changes. Changes in Earth's orbit, we will explore a little bit more in details. Changes in the sun's strength, because this is something that we poorly understand. You know, the solar activity is not constant. We know that it's varying. We know that there are some cycles in that, but these cycles are mostly still unknown. We cannot make predictions. And to be able to make prediction would be extremely useful, because not only it would allow us to understand better what is causing global warming, but especially it would allow us to understand if in the future we can expect a kind of compensation. This would be extremely useful if we could expect a compensation, a decrease in solar activity following the greenhouse effect. This would be useful because it would allow us to better allocate the resources for mitigation and adaptation. And keep in mind that what we are interested in trying to understand is the evolution of the state of the Earth system, because when the Earth system, we already mentioned this, get in disequilibrium, it may converge to another form of equilibrium, which we already experienced in the past. No ice caps, presence of ice caps, and this different state of equilibrium may last for a long time. And this might be the reason that caused these changes in climate in the past. We don't know, but it may have been that a critical event like a volcanic eruptions increased the concentration of gases in the atmosphere, extended volcanic eruptions, which means an increase of temperature, which may have caused the melting of the ice cap, and consequently a long time to recover, a long transitional time. This is what we are trying to understand, actually, if there have been, what have been the causes. Now, it's, I would like to make a mention to the Milankovitch theory of astronomical forcing of quaternary climate oscillations. This is a relevant contribution to try to understand the oscillations that characterize the quaternary, the period where we are living now. And Milutin Milankovitch has gave extremely important contributions. He's relatively recent. You see that he was born in 1979 and he died in 1958. And he explained the long-term paleoclimatic change during the quaternary. So he tried to explain the glacial versus interglacial periods with changes in the Earth-Sun geometry, changes in eccentricity, obliquity, and precession. Let's try to better understand what they are. And let me see if in the next slide, yeah. So what is the eccentricity? The eccentricity is eccentricity of the Earth orbit with respect to the Sun. So if we indicate with P the perihelion and with A the aphelion, which the perihelion is the minimum distance of the Earth orbit from the Sun, and the aphelion is the max distance, we can compute the eccentricity with the relationship that you see on the left. It is very simple. And this eccentricity is changing a long time due to with a cyclical period, which, if I well remember, it's about 25,000 years, and which is due, this periodicity, to the attracting forces between the Earth and the other planets. So there is a reciprocal attraction among the different planets that changes this, changes the eccentricity with a period, with a regular period of, if I well remember, 25,000 years. And then there is the obliquity, which is the inclination of the Earth's axis, which we know that it's undergoing regular changes, which are also due, as I said, to plate tectonics. It may be due to the impact of asteroids. And these perturbations may cause a periodic change of the inclination of the terrestrial axis. And then there is the precession. And the precession is, let's have a look at the web page to define it. So I am more precise. It's a change in the orientation of the rotational axis of a rotating body, like you see here the example of the gyroscope. So it can be defined as a change in the, okay, let's look at, let's forget about the details. We are not interested in the details. But what is important to know is that the precession also originates a periodic change of the exposure of the Earth to the sun radiation, a periodic change which may cause periodic also changes in climate. Here we have a video which I would like to, sorry. Let's see if I can open it directly. I was not lucky, but I think that this time, yeah, we get it. 1 second. Isn't available anymore. I see. Okay, this is not available anymore. Let's forget about it. Okay. Now, basically, what we are trying to understand is the details of this picture, try to understand these cyclical variations, and the contribution of Milankovitch gave a significant input in trying to define these periodicities. But still, even with the contribution of Milankovitch, we cannot explain the details, the fine details of the changes that we experienced in the recent period, which is marked here with agriculture and the civilization. Now, let's make a final focus on the great acceleration. So the very recent period where, as we know, we got an increase of CO2 concentration, and we got also an increase of emissions, and therefore the greenhouse gas, and therefore the global warming. So in this period, we can still recognize, if we look at the period after 1950, some inhomogeneities of the general tendency of temperature and other climatic variables. So we can still see, even in the past 50, 70 years, the presence of periods where temperature didn't increase, even if the CO2 emissions were steadily increasing. And we can identify irregularities which we cannot explain. We can still not explain, or we can postulate some reasoning, some explanation, which, however, don't give a final answer. For instance, the temperature didn't increase between 2004 and 2014. The global temperature was more or less stable. And then we had a sharp increase in 2015 up to 2019. And then in the past 4 years, again, a stabilization. It's not really clear. Some scientists postulate that maybe the reduction of emissions during the COVID period caused the recent stabilization, but it's not a credible explanation because the climate system has an inertia. And therefore, we are still wondering, even in a world that is highly monitored today, what is the reason for this recent fluctuation, recent irregularities? And now let's look at the predictions. The predictions you see here, we have a progress of temperature from 1700 to today, and a prediction up to 2100. And you see that there are these short-term irregularities. And here I am quoting a conclusion of the fifth assessment report of the IPCC, the International Panel on Climate Change, which says that anthropogenic influences have likely affected the global water cycle since 1960 and contributed to the retreat of glaciers since the 1960s and the increased surface melting of the Greenland ice sheet since 1993. Anthropogenic influence have very likely contributed to Arctic sea ice loss since 1979 and have very likely made a substantial contribution to increases in global upper ocean heat content and to global mean sea level rise observed since the 1970s. What is important to stress here, it's not really the concept, because what is stated here is well known also by us. What's important to stress here is the presence of these terms, likely, very likely, or the last report used the terms high confidence, low confidence, medium confidence, which emphasizes on the one hand the presence of uncertainty. So basically, we observe these changes. We believe it's coherent to assume that these changes are caused by increased CO2 emissions, human activity. On the other hand, we are not sure. And another thing that is important to notice here, the use of these terms highlights that a quantitative assessment of uncertainty is not possible, because otherwise they would say with the probability of 8%, not very likely, because very likely it's a synonym of high probability, but it's a non-quantitative synonym. If we were able to quantify uncertainty in quantitative terms, we would say it's with the probability of 80%, the sea level rise is caused by anthropogenic influence. Here they use very likely, which is non-quantitative. And because they recognize, and also if you read the IPCC report, there is a long discussion on uncertainty. They recognize that there are these unknowns that don't allow us to reach a final conclusion. So let's assume now that these predictions that you can see here, the same figure here, these predictions, what you see from now to 2100 is predictions. And these predictions are corresponding to the worst case, the red line, and the best case. These cases correspond to different level of CO2 emissions and different level of confidence of models. And with the bands, it's indicated a qualitative assessment of uncertainty. It's not a quantitative assessment. So what will happen and in particular this slide consider the situation of alluvial and coastal systems, which are the more sensitive environments, because they are located in front of the sea. They are subjected to two possible kind of floodings, fluvial floodings and coastal flooding. And also they are very delicate ecosystems. And here they focus on some places in Italy. You see the figure on the upper right. And indeed, we see that there is for these regions, these are limited spots, but still they are important regions. There is a potential risk of drowning in the scenario of 2100, which once again, if you consider the whole trajectory of our discussion today, that there is an overall variability which we don't understand, which may superimpose with this changes that we are predicting, which are based on human influence, human emissions. Therefore, it's pointing out once again the need for understanding some more, because we need to put together the geological record, which is the unique, tangible record of expected future coastal scenarios, with the model predictions. And in order to understand more the capability, the ability of different societal and environmental systems to react to future changes. Are they compensating? Is the local asset, the local system compensating for changes, or are we transitioning towards a new equilibrium, which may be a warm period, which may last for millions of years, with temperatures that are 5 degrees higher than today? This is possible. Understanding the climate of the past is the key to making future predictions. And this is the last slide with a citation to Winston Churchill. The further backward you can look and the further forward you are likely to see. So this can be considered like the moral of the story today. I understand that I didn't give you a solution, but I hope that I was able, thanks to Professor Rossi, to give you an overview of the current research and the motivation why we need to better understand the past. Any question? Okay, so we will see each other on Monday, and then we will have the Easter break and one final lecture. Thanks.